We look up every day, and we see power lines, communication cables, an entire web crisscrossing our world. They're so ubiquitous, we barely even notice them.
It's true.
But what if I told you there's an entire meticulously constructed universe of incredibly precise rules governing every single wire, pole, and attachment?
It really is a hidden world up there.
Today, we're taking a deep dive into the surprisingly complex world of overhead line regulations. We're sifting through stacks of official documents, definitions, construction standards, maintenance requirements, you name it. We want to uncover the hidden logic that keeps our modern world running safely.
Yeah, it's a truly fascinating look at how meticulous planning and, strict adherence to detail translate into the reliable and safe infrastructure we all depend on. Our mission in this deep dive is to reveal the why behind what often seems mundane, giving you a shortcut to understanding the critical engineering and regulatory principles that are quite literally over your head.
Okay, let's unpack this. So, to truly appreciate the complexity of these systems, we really need to understand the language they speak. The first thing that jumped out at me from these documents was the sheer detail in the definitions. It's not just a wire or a pole, is it? There's like a whole specific vocabulary.
You're absolutely right. Every single component has a precise functional definition because each plays a very specific role in ensuring both safety and, seamless operation. What's truly fascinating here is how these definitions clarify crucial distinctions that have significant real-world implications.
Like with cables. My initial thought would be, it's just a cable. But these documents make a big deal about different types of fiber optic cables.
They do. For instance, there's fiber optic cable communication versus fiber optic cable supply, a distinction often based on their intended use or maybe proximity to high voltage lines. But even more granular, we encounter dielectric fiber optic cable facility, where dielectric simply means it's an insulator containing no metal or conductive parts.
Ah, right, no metal.
Exactly, versus non-dielectric fiber optic cable facility, which does contain conductive elements.
Okay, so for those non-dielectric ones, the ones that conduct electricity, how do they handle that? Is it just simple insulation, or is there like a sophisticated strategy to prevent, say, your internet cable from accidentally carrying power line voltage?
Oh, it's far more sophisticated than simple insulation. They must be electrically isolated. This means the conductive parts are carefully conditioned to prevent any unintended transfer of system voltages from one circuit to another. Imagine preventing a surge from a power line from frying communication equipment or, worse, harming a worker.
Right.
This isolation can be achieved through electrical or mechanical methods. A powerful example of a mechanical method given in the rules is not less than a 15-inch minimum gap, used in conjunction with a non-conductive closure.
15 inches, that's quite specific.
It is. It's a critical safety buffer, engineered to account for even extreme conditions like high humidity or an unexpected voltage spike.
That kind of precision for safety is eye-opening. And circuits aren't just circuits either, are they? I saw categories that seem pretty nuanced.
Indeed. Take Class C communication public and private circuits. These aren't just for your telephone line. They can include railroad signal systems, data lines, clock networks, fire or police alarms, even cable television. But they come with incredibly strict operating limits, typically not exceeding 400 volts to ground or 750 volts between any 2 points, and with transmitted power not over 150 watts if the voltage exceeds 150 volts.
150 watts, okay.
The critical point is if a circuit primarily used for information transport exceeds these values, it's immediately reclassified and must meet all the rigorous safety and construction requirements of a full-blown supply circuit.
Wow.
That's a massive regulatory jump for what you might think of as a relatively low-risk line.
That's a huge leap in categorization, even for a data line. And I imagine that hybrid idea extends to other specialized circuits, like railway signal circuits, which must walk that fine line between communication and power.
Precisely. Railway signal circuits are considered communication circuits, or Class C, if they operate at less than 400 volts to ground. However, if the voltage between conductors exceeds 150 volts, the power transmitted cannot exceed 150 watts.
Same threshold.
Right. Fail to meet those specific criteria, and bam, they're treated as full supply circuits. It highlights how the function and potential risk determine the regulatory burden.
Beyond communication lines, the sheer power in supply circuits is intimidating. What truly struck me was how these are meticulously categorized by voltage. Take Class E, for instance, specifically. 300,000 volts or more between conductors. That's an extraordinary amount of power. What's the regulatory philosophy behind these distinctions? And how does that influence their placement or construction compared to lower voltage lines?
That's a vital question. These voltage categorizations are fundamental because they directly dictate the required clearances, insulation, and structural strength, ensuring public and worker safety around these high-energy systems. And it's not just about what flows through them. Even the definition of a conductor is brought in to mean a material suitable for carrying electric current or transmitting light, like fiber optics.
So you can't just wrap a wire and call it good. I notice the rules talk about insulated conductors or cables. Suitable.
Yeah.
What does suitable really mean there? Because apparently a weather-resistant covering doesn't cut it.
That's entirely correct. Suitable is a very specific term here. It means the insulating material's dielectric strength. Its ability to resist the flow of electricity must be sufficient for the maximum potential voltage the conductor will carry. A weather-resistant covering is just that. Protection from the elements, not a reliable electrical barrier. It's a critical distinction for safety.
That makes perfect sense. Given the precision for wires, is a utility pole just a utility pole?
Mm-hmm.
Or do the regulations distinguish between different types of poles and how they're constructed or used?
Oh, there are definite distinctions. For example, a non-climbable pole is defined by its smooth exterior surface, absence of pole steps, and the requirement that work on it must only be performed from aerial lifts.
Ah, so you literally can't climb it.
Right. It's a design choice driven entirely by worker safety. And then you have pole restoration techniques, which is the application of material to a pole to restore its structural strength. It highlights that even existing infrastructure is subject to rigorous standards to ensure continued integrity.
And it's not just about physical components. Even geographical areas have incredibly precise definitions, like districts.
Yes, you have loading districts like heavy and light, which dictates structural requirements based on expected wind, ice, and snow loads. And then there's the incredibly important high fire threat district, which is comprised of Zone 1 from the USFS and CL fire tree mortality high hazard zones, and Tier 2 and Tier 3 of the CPUC fire threat map.
Okay.
For you listening, this classification directly impacts fire safety protocols in California, highlighting the profound life and death implications of these seemingly technical definitions.
It's clear that the definitions are meticulously crafted.
Mm-hmm.
But how do these intricate rules actually translate into the day-to-day reality for utilities as they build and maintain these systems? My impression is that there's a profound emphasis on collaboration and proactive prevention baked into the very core of these regulations.
That's an excellent observation. These rules establish a comprehensive framework for safety, reliability, and the efficient use of shared spaces. If we connect this to the bigger picture, it's about minimizing risk in a constantly evolving urban and rural landscape. Rule 31.1, for instance, dictates design, construction, and maintenance. It states that systems shall be designed, constructed, and maintained for their intended use, following accepted good practice for local conditions.
Accepted good practice.
But here's the crucial part. If circumstances demand a higher standard for safe, proper, and adequate service, that higher standard must be followed, even if it goes beyond the specified rules.
Wow.
It's an overarching directive for proactive safety, always minimizing interference and avoiding unusually dangerous conditions.
So it's about doing what's necessary, not just the absolute bare minimum. What about avoiding conflicts between different lines or utilities? It seems like a recipe for chaos otherwise.
It absolutely would be. Rule 31.3 addresses avoidance of conflicts and crossings. It mandates efforts to avoid conflicts, actively encouraging joint pole construction where possible. There's a specific rule that high-voltage Class H circuits shall not occupy both sides of a thoroughfare unless special permission is obtained from the Public Utilities Commission or, mutual consent is filed. It's all about managing complex shared infrastructure.
And speaking of joint poles, is that always allowed? Can any utility just decide to put their lines on someone else's pole?
Not at all. Rule 31.5, joint use of poles, states that while utilities should consider joint use to minimize infrastructure footprint, the consent of the owner is always required.
Always need permission. Makes sense.
It also has a fascinating specific restriction. Non-climbable poles in partial underground distribution systems shall not be jointly used. This rule protects the specialized safety protocols and work methods associated with those particular poles.
That makes sense. But what about when lines are no longer needed? Do they just leave them up there? I feel like I've seen inactive lines just hanging around.
That's a great question. Rule 31.6 on abandoned lines requires that lines or portions of lines permanently abandoned, meaning no foreseeable future use, shall be removed by their owners.
They have to remove them.
Yes. This isn't just about aesthetics. It's
Oh.
explicitly to prevent them from becoming a public nuisance or a hazard to life or property.
Huh. A public nuisance. Have you ever considered that a dead wire could be a public nuisance?
That was a genuine aha moment for me too, reading that. I'd never considered the visual clutter or long-term hazard of just leaving inactive infrastructure in place. It really speaks to the comprehensive nature of these rules. It's a proactive step to keep our environment safe and uncluttered.
So if multiple systems are involved, like a new communication line going up near an existing power line, how do they decide who's responsible for maintaining clearances or making adjustments?
That's where Rule 32.1, two or more systems, comes in with a foundational principle. The owner or operator who last in point of time constructs or erects facilities is responsible for establishing the required clearance from previously erected facilities.
Last one in is responsible.
Okay.
It also states that subsequent entrants shall recognize the provisions for future development made by all prior entrants. This means you can't just build wherever you want without considering the long-term expansion plans of existing lines. It's about orderly and, well, considerate infrastructure development.
That sounds like good planning. And what about the physical arrangement of the lines on the poles, especially with different voltages? Is there a general hierarchy?
There absolutely is. Rule 32.2, relative levels, sets a general principle. Higher voltage circuit shall in general be carried at the higher level. This is a fundamental safety measure, placing higher risk elements further out of reach.
Higher up, higher voltage. Got it.
However, there are exceptional cases under Rule 32.2G where this can be reversed, provided the lower voltage circuit meets the same strength requirements as the higher voltage circuit would normally require.
Ooh, really? So a low voltage line could be below a high voltage one? Potentially, yes, but only if it's built to be just as strong as the high voltage line should have been in that position. This raises an important question. What kind of engineering goes into making a lower voltage line as robust as a high voltage one? It's a significant undertaking to ensure that kind of structural integrity.
That's a massive design consideration. And what about when circuits of different classifications actually share the same crossarm? I imagine that's a whole other level of precision needed to prevent contact.
It is. Rule 32.4 details incredibly precise horizontal separation requirements. For instance, if you have very different supply circuits, say 750, 7,000 over 500 volts and over 20,000 volts, on the same crossarm, they must be on opposite ends with a horizontal separation of not less than 36 inches between the nearest conductors of different classifications.
3 feet apart.
Right. And for communication circuits and lower voltage supply circuits of different ownerships on the same crossarm, the separation is not less than 30 inches. These are not arbitrary numbers. They are calculated to prevent electrical arcsing or accidental contact, safeguarding both systems and the public.
Makes sense.
There are even specific exceptions, like on transformer structures, where bus conductors, the main distribution lines of different voltages, can be supported on opposite ends of the same timbers under very specific conditions, demonstrating the engineered balance between safety and operational necessity.
We often don't think about the unseen safety measures, like what happens underground or what isn't allowed on poles. How do these rules manage that?
This section really highlights the proactive measures taken to prevent hazards. What's truly fascinating here is the absolute clarity on what's permissible and, more often, what isn't and why. Take Rule 33.2, ground or earth as a conductor. It clearly states that ground or earth shall not be used as a normal return or circuit conductor.
Wait, really? I always sort of assumed the earth was part of the circuit.
It's a common misconception, but no, it's only permitted for stabilization and protection, like giving lightning a path to dissipate safely.
So that aha moment, realizing the earth isn't a constant, reliable return path for electricity is huge. It completely changes how you think about grounding. So what exactly constitutes an effective ground under these rules? I imagine it's more than just sticking a wire in the dirt.
You're right. It's incredibly precise. To be effectively grounded, there's a strict electrical standard, an impedance of less than 25 ohms, essentially ensuring electricity can safely and quickly dissipate into the earth.
25 ohms. Okay.
If that's not naturally achievable, the rules mandate a specific physical configuration. Imagine two robust, corrosion-resistant metal rods, precisely sized, at least 12-inch in diameter and 8 feet in length, and driven deep into the ground, a minimum depth of 8 feet at not less than 6-foot centers, interconnected with a heavy-gauge copper wire.
Wow, that detail.
This detailed specification isn't arbitrary. It's engineered to act like a high-speed drain for any stray electricity, providing that crucial path to safety during a fault or lightning strike, preventing electrocution or damage. The rules also clarify that independent ground connections are generally not interconnected, except in common neutral systems or specific cases involving lightning arresters designed to localize any electrical issues.
Now, this next one I found incredibly interesting because you see it all the time and probably never consider the implications. Foreign attachments. All those flyers, signs, decorations.
This is absolutely crucial, and it's a rule driven by safety. Rule 34 states, nothing in these rules shall be construed as permitting the unauthorized attachment to supply street light or communication poles or structures of antennas, signs, posters, banners, decorations, wires, lighting fixtures, guys, ropes, and any other such equipment foreign to the purposes of overhead electric line construction.
So basically anything that isn't near the utility system.
Pretty much. The rule emphasizes that owner consent and commission approval are required for permanent attachments.
So all those yard sale signs or missing pet posters, they're actually unauthorized. That's a real-world consequence that most people probably don't consider. But what if there's an approved temporary attachment, like a city banner for a festival? Are there still rules?
Oh, yes. There are incredibly specific rules for approved temporary attachments. For supports, messengers, and span wires can be used, but never the utility's own conductors, cables, or messengers themselves. These supports must have sectionalizing insulators.
Breaks in the wire.
Essentially, yes. Built-in breaks in the conductive path strategically located 6 to 9 feet from the poles, preventing electricity from traveling along the support structure itself. If rope is used, it's only for non-energized banners and decorations for short periods. It must be securely tied with all excess rope removed and not contact or obstruct any pole steps.
And there's even a rope strength requirement.
Yep. Minimum strength. 200 pounds, which is equivalent to 38-inch manila rope. This isn't about being a spoilsport. It's about ensuring safety for utility workers who need clear access and preventing dangerous entanglements or hazards to the public.
And what about climbing space for utility workers? That's got to be protected.
Absolutely. All apparatus shall be installed outside of climbing space. There's only one very narrow exception. Temporary pole bands or ropes can be in the climbing space, but they are limited to 6 inches in width and no more than 1 in any 24-inch section.
Very limited.
Exactly. Clearances are also strictly defined. Energized apparatus must maintain the same clearances as a standard 0750V service drop. That's the low-voltage line bringing power from the pole to your house. For non-energized apparatus, there's a 6-foot vertical clearance below any energized conductor and a 1-foot radial clearance from streetlights or communication cables.
It all ties back to safety and keeping the system working.
Precisely. This isn't arbitrary. It's all engineered to ensure worker safety and the consistent, reliable operation of the system.
Finally, let's talk about the constant dance with nature. How do trees, wind, and even temperature play a role in these rules? Because that seems like an ever-changing challenge.
This area is a great example of how these rules manage very real, dynamic environmental factors that could otherwise severely compromise safety and service. Rule 35, vegetation management, has the primary goal of safety and reliability of service. It requires maintaining necessary and reasonable clearances between line conductors and vegetation, referencing extensive engineering tables that detail precise measurements based on voltage and environment.
So not just hacking away, but specific distances.
Exactly. It also explicitly requires the removal of dead, rotten, or diseased trees or portions thereof that overhang or lean toward and may fall into a span if the utility has actual knowledge of them. It's not just about what's touching the wire, it's about anything that could potentially fall into the lines.
So it's about preventing potential hazards from falling branches, not just trimming what's growing into the line. What about for lower voltage circuits? Do they have different standards for vegetation contact?
For low voltage circuits, 750 volts or less, the rule distinguishes between abrasion, which is damage from friction, and scuffing polishing, which is not considered abrasion. If a circuit shows strain or clear evidence of abrasion from vegetation contact, that condition must be corrected, as it indicates a potential weakening of the line.
Are there any exceptions to these vegetation management rules? It seems like it would be incredibly difficult to get permission to trim every single tree, especially on private property.
There are crucial exceptions. One is where trimming isn't practicable. In those cases, for circuits less than 60,000 volts, conductors can be separated from trees with suitable materials or devices to avoid abrasion or grounding.
Like putting a protective sleeve on the wire.
Something like that, yes. Another significant exception is the good faith effort rule. If a utility makes a good faith effort to obtain permission to trim or remove vegetation, which means documented attempted personal contact plus written communication, but permission is ultimately refused or unobtainable, the utility is not compelled to comply with that suitable materials devices exception.
That's a critical distinction. It sounds like the utility has to do their part to request permission, but they're not forced into an impossible situation if denied. So what does happen if permission is refused? Is the utility still held liable if something goes wrong with that specific tree?
That's an excellent follow-up question, and it speaks to the limitations of their power. If the utility has made a documented good faith effort and permission is refused, their liability for that specific tree's impact on the line can be mitigated as they've met their regulatory obligation to seek permission for the necessary work. It sort of shifts the onus back to the property owner who refused access.
Interesting dynamic. And I saw something about mature trees, too. Do old, strong trees get special consideration?
They do. There's a mature tree exemption. Trunks and major limbs located more than 6 inches from conductors, but less than the full required clearance, are exempt if they have sufficient strength and rigidity to prevent encroaching on that 6-inch minimum clearance under reasonably foreseeable wind and weather.
But the utility has to make that call.
Exactly. Crucially, the utility shall bear the risk of determining whether this exemption applies. So the onus is on them to make that complex judgment call, balancing the tree's health with public safety.
Finally, how precise are these minimum clearances in general? It sounds like they're not just estimates, but the environment can change so much.
They are incredibly precise, and that's why the rules specify standard conditions for measurement at a temperature of 60 degrees Fahrenheit and no wind. This ensures consistency, regardless of when or where the measurement is taken.
Standard conditions, okay.
These are not mere guidelines. The rules set incredibly precise limits on how much these clearances can be reduced typically by a small percentage, like 5% or 10% for most scenarios, but absolutely no reduction for critical clearances, like those over major thoroughfares, which are set at 22.5 feet.
No wiggle room there.
None. Clearances are measured from surface of conductors for anything less than 5 inches, and from the center lines of conductors for 5 inches or more. And importantly, the minimum clearance applies to the specific location under the span being measured and not for the entire span. Every single point along the line matters.
Phew. What a deep dive into the almost invisible rulebook that keeps our power and communication flowing. It's truly eye-opening to see the meticulous detail that goes into every aspect of these overhead lines, from the exact definition of a cable to the specific strength of a rope holding a temporary banner. It transforms what we take for granted into, well, an engineering marvel.
These aren't just arbitrary regulations. They are distilled wisdom from years of engineering, incident prevention, and collaboration. They represent a constantly evolving framework, refined through experience and rigorous analysis, all aimed at ensuring public safety and system reliability. We've taken a seemingly dense set of documents and hopefully found the core nuggets that illuminate their profound real-world impact.
You've now got a whole new perspective on the infrastructure above your head. For your final thought, consider this. Given the extraordinary level of detail and foresight embedded in these regulations, for something as seemingly simple as a utility pole and its wires, what other foundational, highly regulated systems exist in our daily lives that we rely on constantly but never truly understand?